Go.
Good morning, ladies and gentlemen. This is an AP for response question.
It is.
Go ahead and read through it and give it your best shot.
Pause the video. Well, I'll read it. A student holds one end of a string in a fixed position. A ball of mass 0.2 kilograms attached to the other end of the string moves in a horizontal circle of radius that much with a constant speed of that much. How much work is done on the ball by the string during each revolution? Go ahead. A, B, C, D, or E.
Okay. So start off with a sketch. Okay, I'm looking down on the action here, the horizontal circles. And let's just go ahead. So work is force times the displacement, yes?
So that's the ball. What's the direct? It's going around a circle, and you've stopped it. You've taken a picture of it and stopped its motion.
So what direction is the force?
Well, it's centripetal. What does centripetal mean?
Well, it's going to be
toward
the
the center.
And it's going in a circle like this, but at this moment, what is the displacement?
The instantaneous velocity is along the tangent.
Okay, so that's like this.
Yep.
Cosine of 90 is 0. So what should our answer be?
A.
A. There's no work done here.
It's perpendicular.
Hard to believe, but it's true. All right, so let's talk about Kepler. So yesterday we looked at our planetary motion little model thing, right? And Kepler found the geometry of planetary motion. He took someone's data and he
spent years and years and years doing calculations.
And we got this.
Yep.
So then Newton, he really was tremendous in terms of the advancement of our understanding of the universe. Kepler was able to find the geometry of the planetary motion, while Newton explained why this was all possible.
Yep.
Why it happened.
Yep.
Newton explained Kepler's law with his own laws of motion and his law of universal gravitation. We know this one, right?
Yep.
Okay. The relationship between distance and speed in orbit occurs because the force of gravity is stronger, closer, and weaker further. So remember yesterday when we were looking at the planetary orbital model, right? And the white planet in the middle and the ones in the middle were going faster,
yep.
right? They were beating the other ones around.
Yep.
This is because gravity is stronger closer to the sun.
It has to go faster, it'll fall into the sun because gravity's stronger.
It's got to have that, the gravity's pulling it in, so it has to have enough speed this way to pull it out.
That's right. And if it's farther out, the gravity is weaker, so it doesn't have to go as fast.
Yeah, exactly. Okay. So a couple lessons ago, we showed you this equation. The centripetal force is equal to the force of gravity.
The thing that's making it go around is gravity.
Mm-hmm.
Well, what's centripetal force?
Well, the centripetal force is represented by, mass times acceleration.
Yep.
And this acceleration, if you remember, we have a couple different equations, right? The centripetal acceleration is v squared over r.
Yep.
And so I just replaced that right here. Instead of putting centripetal acceleration, I put v squared over r. And it equals...
Newton's law of universal gravitation.
Yeah.
By the way, what are these variables, Ms. Mo?
Oh, okay. So a big G is our constant. Big M is the mass of whatever's in the center.
Yep, whatever the thing's going around.
Yeah, whatever it's going around. And this is the radius between the two centers of mass.
Yep.
And this is the mass of the other
thing that's going around.
And it looks like the mass is... Okay, we'll come on.
Let's just see what happens.
Okay. So here we go. We've done some work here.
We can simplify this.
Yeah. And if we wanted to solve for velocity, we could, right?
Well, before I would do anything, I'd do this canceling.
Yeah, so you know that these are going to cancel out, and one of these is going to cancel out. This is going to cancel out with one of these. And so, you're really left with something that's not too complicated.
Does it show you that in the next one?
No,
go back for just a moment. What I would say is that notice that the square of the velocity is the inverse of the distance. So if the distance is small, the velocity is large. And if the distance is large, the velocity is small.
And that makes sense. That's what we just talked about with the
Yep.
planets.
Yep,
Right?
yep,
I'm going to write this on the board because I think we're going to use it next.
yeah.
G, and then we're going to go big M over R.
Yep.
Okay. What is the moon's velocity in its orbit around the Earth?
Yeah, well, we need the mass of the Earth,
So moon, Earth, it's going
and
on
we need
like
the
this,
orbital
right?
radius of the moon.
So mass of the Earth, you've got it, and you've got the radius of the moon. Okay, it gives. Oh, I remember these numbers. What?
24 kilograms.
Oh, I didn't remember this one though.
No, me either.
Good thing we gave it to you. Okay. All right. So we want to know the velocity. What do we have to do to this?
Well, you're gonna take the square root of both sides.
Okay, velocity.
And boys and girls, you should be writing these numbers down in your notebook
yeah.
as you go along.
What was the G? It was a
6.67 times 10 to the negative 11 Newton meters squared over kilograms squared.
Whew. Okay, good thing I've written that a million times.
Hey, it took me 10 years to memorize that thing.
All right, let's plug it in. So it's going to equal 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times, this is a big M, mass of the Earth, that's what it's going around, 5.98 times 10 to the 24th kilograms, and I have to divide it all by this is going to be scary. The radius, wait, this is just the radius of the moon though.
It's the distance of the Earth to the moon. Yep,
Right
that
there.
R right there.
There we go. I was like, hold on, do it to do something extra.
It's not how big the moon is.
Yeah,
That's
yeah.
a different radius.
Okay, so let's see. So how are we gonna put this in our calculator? I think we're just gonna put it straight across, right? Just like a sentence.
Yeah, I think it'll work.
Let me see if I can. Can you see me okay from that?
It's hard to see the screen, but no,
Yep.
you're fine. Go ahead.
Okay, look at. Sometimes it likes to do that to me. Okay. All right. So we got square root. So I'm gonna go ahead and just write it as is. 6.67 e to the negative 11th times 5.98 e to the 24th, and I'm just writing it just
Then
like
just
I'm saying
divided
it.
by it, yeah.
Yeah, just divided by 3.48 times e to the 8th. Mine looks like this before I put it in.
Yeah, that should be right.
Okay. So my velocity is going to be 1,070.6. We'll just call it 1,071 meters per second. 1,007. I say 76. That is 71. Okay, meters.
So where do you aim your gun if you want to hit the moon?
Yeah, right.
You know, where do you aim the rocket if you want to hit the moon if it's going around at that
That's
speed?
got to be tough. That's rocket science.
That's rocket science right there, baby.
Okay. So. Oh,
Here's the same thing, except
A
what's
little
different here,
different.
boys and girls?
So we have traded out the v squared over r for our next advancement here. For velocity, we just plug this into here and we get this 4 pi squared r over t squared.
Sweet.
Put it right there, boom. And why would we want this instead of the other one?
Well, this has got something the other one didn't have, and it's the period. This has the period in it.
Yeah, so if we ask about the period, you need to know that you got to find this.
Yeah.
You got to use this.
Just before you change the slide, boys and girls,
Oh, yeah.
if you wanted to solve this for r, or if you wanted to solve this for t squared, what would it look like? Go ahead and show them.
What would you do?
No, it's on the next
Oh,
slide.
it's on the next slide? Oh, you're right. Bada boom. That's how you do it.
Remember what Kepler said was the square of the period is proportional to the cube of the radius. And so remember yesterday we had the planet A and planet B. With Newton, you don't need planet A, planet B. There is a constant of proportionality. Yep. The top part is the geometric, the bottom part is the Newtonian law of gravitation.
And now that we have this, could you solve for every variable?
Yeah. Solving for t is easy. Take the
Easy.
square root. But boys and girls, could you solve for, you don't have to solve for 4 or pi squared, but m, could you solve for r, m, and
Yeah, those are
capital
things
T?
you need to be able to solve for.
T is the period, r is the orbital radius, and m is the mass of the thing in the middle. Go ahead.
Okay, here we go. A satellite dish always points at the same spot in the sky. Why?
Huh.
Well, if it's pointing at the same spot in the sky, that means it's moving with Earth at exactly every second of every day, right?
Well, it's pointing at a satellite, right?
Yes.
So that's why they call it a satellite dish. It's pointing at a satellite that's in the sky, and it's always at the same point in the sky.
Yeah, so it has to orbit with it. So essentially what we're going to have here is we are going to have this satellite with the same exact period as Earth's.
Earth's rotation.
Yeah.
How long does it take the Earth to go around once?
In hours or seconds or minutes or what?
Well,
24 hours, right?
1 day.
Yeah, 1 day.
24 hours.
Yeah.
How many seconds in 24 hours? See, 24 times 60 minutes in an hour times 60 seconds. I think it's 86,400 seconds. Now, Mr. Boykin's saying that because it took me many, many years of doing it over and over again.
Do something enough times, it becomes a muscle memory.
Yeah.
Okay, so let's go to our next slide here. A geostationary satellites orbit at a specific altitude. What is it?
While she's doing that, what does the word geostationary mean?
Doesn't geo mean like Earth?
Well, what does stationary mean? It means not moving, and geo is like the Earth, so it doesn't move from a spot above the Earth.
Okay, so orbits at a specific altitude around Earth, right?
So what is it we're trying to solve for here, Ms. Mo?
Well, we want the altitude. That's going to be basically the radius, right?
Radius.
Because we've got the satellite and we've got our lovely planet Earth, like this, right?
Yep.
Okay, and we know that our big mass is going to be the mass of whatever is in the center.
Yep.
So the mass of the Earth, which you said was 5.98.
Times 10 to the 24 kilograms, I think.
Okay, and then we're trying to figure out what the radius is.
Yeah.
Okay, so let's go ahead and do some algebra here. So what we can do is I'm going to put this on this side. Instead of doing all the multiplication division, I'm just going to flip it.
All right.
T squared times GM over 4 pi squared.
You understand what she's just done, boys and girls? And she's divided both sides by what's in the parentheses.
Yeah.
And rather than put it on the bottom of the t squared, she just flipped it over.
And I'm going to go ahead and just take the cube root of this now.
Cube root, oh my God, oh my God,
Oh my God, what are we going to do? Well, let's plug it into the calculator. Okay, so 3 times the cube root, let's put our numbers in. What is our period of the Earth?
The period of rotation is 86,400 seconds.
86,400
No. 86, comma.
have you guys haven't figured out that Miss Moore is not good with large numbers?
No. It's early in the morning, boys and girls.
86,000. I have a hard time both reading large numbers,
Seconds.
so seconds. And then our G is 6.67 times 10 to the negative 11th. Newton meter squared over a kilogram squared.
Yep.
It's been a little longer there. Times our mass, which is 5.98 times 10 to the 24th.
And you don't have to put parentheses here. You could just have the whole thing divided by 4 pi squared.
Let me get rid of those because I don't want to confuse you guys. And then the whole thing, right? I can just put the whole thing
Divided
under
by
it.
4 pi squared.
4 pi squared. Yeah. Let's get rid of those. Okay. I'm going to go ahead and plug it in. And again, just like a sentence, at face value, we'll just plug it
Okay,
in.
now where do you find that cube root? That's lives under the math
The
button.
math button. So we've got 4. Okay, so hardest part is over, right? Okay, 86400 times 6.67 e to the negative 11th.
You're doing this at the same time, right, boys and girls?
Times 5.98 e to the 24th.
29.
Oh, 29? Wait for the math.
Oh, it's 24. No, it's 24.
Close one. Okay, divided by 4 pi squared.
Now you may need to
that's
put
not squared.
parentheses around that 4 pi squared.
You think so? Okay,
Yeah.
I'll go ahead and make that change.
Just move it back and
Like this.
yeah, 4 parentheses 4 pi squared in parentheses.
And let me go plug it in there. Here we go. We're trying to find the radius. This number looks probable, right?
What do you got? I can't see.
It's 955,711
Meters.
meters. Actually, 712. So this is the radius. So our radius equals 955,712. We'll call it like that, meters.
So there's a band around the Earth's equator at that distance from the center of the Earth. Somebody's trying to get in.
Oh, Miss Leonardo! I didn't knock. That's why I went.
Hi, Miss Leonardo. Say hi to AP
Hi.
Physics. All right, let's finish
Hey,
this.
Pete, physics. I just want to grab a water bottle.
Oh yeah, it's over
Did I
there.
interrupt?
No, you're good. You made a special a special guest appearance
Yes.
on our video. Miss Leonardo drinks 1 gallon of water every single day, just like me, and she's having a water issue, so Miss Moore to the rescue. Water! Woo-hoo! Okay. All right. Back to
Okay, so what that means is that that band is crowded full of geostationary satellites at that altitude.
Dang. So there's not just one here, but
There's thousands
Yeah.
and thousands of satellites up there.
So every single satellite that exists that's a geostationary satellite is at that height, which means that our satellites are all pointed. They have to make sure they point at that whatever satellite. they
Satellite
point
dish has got to point at that. So do we have a satellite dish?
to. Oh yeah, it's over there.
Yeah, we're not going to
Yeah.
look at it.
Okay, what is the moon's orbital period?
Which variable are we going to be solving
I'm
for
gonna
here,
leave
boys
this.
and
I'm
girls?
gonna erase this. You should have said, "Ooh, Miss Moore, we're solving for that one."
Now, what do we need? We need the mass of the thing at the center, which I believe is the Earth.
Still the Earth. But now we're talking about the moon. Right? Moon? Yeah.
So,
Okay.
oh, this is easy. We
It
just
is.
take the square root, don't we?
Yeah, so we'll take the square root of this side, square root of that side. We'll say t equals the square root of this.
4 pi squared.
Squared over. And our g is...
And you're going to have to do 4 pi squared r cubed.
Oh, yeah, right up here, right? Oh, and
Yeah.
what's our...
No, it's just r cubed. Oh, the radius. That's right. What
is
was
it?
that?
Oh, I don't remember
Boys
off
and
the top
girls,
of my
you
head.
have it written down.
Let me get out my book here. The radius of the moon,
The moon's.
1.74 times 10 to the 6th.
No,
Is that
that's
right?
wrong. That's the rate. We need the
Oh, in
distance from the
between?
Earth. The distance from the Earth is 3.85 times 10 to the, what is it?
3.8. Oh, right here. Mean distance from Earth. 3.8 times 10 to the 8th. 3.85. Good catch. It's 10 to the 8th, I said?
8 meters.
That's an 8. Okay, divided by my G.
And the mass of the Earth is
0.98.
5.98 times 10 to the 24 kilograms.
We're good, right?
Yeah.
Oh, this is cubed. Right, the radius is cubed.
Why is showing your work worth 1 point and the answer worth 1 point? Because putting this in the calculator is an accomplishment, and you might hit the wrong button. God knows it happens to me, it happens to Miss Mo, it happens to everybody.
Literally always to me. Okay, square root. So I'm gonna go and help me if I mess up here. I'm gonna go 4 pi squared
4 squared
times 3.8 e to the 8th. I gotta cube this.
You could use the caret, I think.
Yeah, you're right. I could. Do we need to put that in parentheses, or are we okay?
No, the top is okay. The bottom you have to put in parentheses.
Okay. When do you have to put it in parentheses? Oops.
Well, because if you don't, it'll divide by the 6.67 and then multiply times the 5.98.
Okay. So 6.67 e to the negative 11, and then times 5.98 e to the 24th parentheses. So the whole bottom part's in parentheses.
Yeah.
Okay, here we go. And I get a period is don't forget it's in seconds.
Yeah.
This really long number. Let's see, 2,330,000.
I've got an idea.
Four.
Divide that by 60.
Yeah.
Divide that by 24.
Oh, 24, yeah, because that way we get it in a day. Okay.
What do you get?
97,103. Is that right?
Okay.
Wait, that was we divided by 24.
No.
We should divide by 6.
First you divide by 60, and then you divide by 60.
So we need to divide by.
Actually, you could divide it by 86,400.
Let's do that. Okay, so dang. Okay, 2, 3, 3, 0, 4, 6, 0.5,
And it
4,
should
3.
be less than a month.
Divide by what was it?
86,400.
86,400. And I get. Oh yeah, there we go.
How many?
I'm gonna call it 27.
27 days.
Yeah.
So
A month.
that's about a month.
A month.
Now understand, as the moon goes around, so does the Earth.
So we took whatever our answer was and we divided by this. So
Seconds
this
per
many
day.
seconds in a day, because we use because period is in seconds.
seconds, yeah.
Seconds, and so technically, if you said
And
seconds,
where do
you'd be
seconds
fine.
live in there? Well, the meters cancel, the kilograms cancel, and you have newtons. And a newton is a kilogram meter per second squared. So seconds comes out of the newtons there. Damn!
Oh, it's really hard.
I'm
when we
almost
have-
worn out. Do we got to do another one?
We do. We've got one more. Aren't you happy? We were gonna let you guys do these on your own.
But we're going to show you.
Miss Moore is like, maybe we should show them. Okay, so if Earth's orbital radius is that, what is the mass?
How do we know the mass of the sun? How do we know the mass of the sun?
How do we know it?
It's through Newton's version of Kepler's third law.
And this is a big deal.
Which one of those letters would be the mass of the sun? Take the square root stuff off of there.
Oh yeah.
Solve this for m. Pause this and solve it for m.
Why is it M? Why?
Because the mass of the thing in the middle. So if we know the period of the Earth, it's 365.25 days in seconds. So multiply the t squared by g. Oh, wait a minute.
We could flip flop this.
Just flip everything
Yeah.
over.
Yeah. Okay. So I'm gonna go r cubed over t squared equals gm over 4 pi squared. I'm gonna put this over here.
Well, that makes it much simpler, doesn't it?
It does.
Just 4 pi squared, you multiply both sides, then divide by g.
Then we have it. That's it.
Okay, now what I would say is, now that's the big idea. That gives us the mass of the sun. Now, you're going to have to take the radius, the orbital radius, which is 1.50 times 10 to the 11, we got that. But you've got to have the period of the Earth in seconds. So that's, Earth goes around the sun in 365.25 days. 365.25 days times 86,400 seconds per day. Damn!
Woo!
Why do they call it scientific notation? Because in science,
Woo.
you have some hella big numbers.
So what you did here, you needed to find the period you need to find the length of time that it takes for the Earth to go around the sun.
Yep.
And we know that it takes 1 day to go, 1 year to go this many days, but we need to get that in seconds.
Yep.
So we multiply by seconds.
You know what,
Right, 'cause
I think
it's
we should
easy.
let the kids plug the numbers in,
Yeah, you guys got this.
and
you
we
know?
should give it up right now.
Yeah, you guys got 4 pi squared. You guys know what the R is.
1.50 times 10
You
to the
know
11.
what G is.
6.67 times 10 to the negative 11.
And you know what T is. Whatever this is.
Whatever that is. On your mark, get set, go!
Answer in seconds. Okay, so your homework, after you finish that, is page 139. You're going to do numbers 32, 35, and 36.
Sweet.